Okay, I think that the full screen means that the speaker is ready to start his talk. And let me introduce our next speaker, Zhao from Shanghai Jiaotong University. So with new result, right?
Yeah, sometimes can you hear me?
Yeah.
Okay. So hello everyone. Today I'm Zhao, and today I will talk about color refinement on digraph. This is joint work with Yao Kun Wu, and for people who are familiar with color refinement on graphs, the most results you will be very familiar. The most results are parallel, but will also be something different. So firstly, I will recall some results on color refinement on graphs. Then I will talk about something on digraphs, which are parallel, and something similar, something different. Okay, let's begin with graph and digraph. For graph, it simply consists of vertices and edges. You may want to consider loops or without loops, but for convenience, let's forget about loops today. But if you want them, you can easily add them to the results. And for digraphs, you replace edges by arcs. So you add orientations in some way, or in other ways, you are considering ordered pair of vertices to be arcs. There is some notation here. We use NU to denote the neighbors of a vertex. And in digraphs, we need to consider all neighbors and in neighbors. So we use N plus for out neighbors and N minus for in neighbors. An isomorphism between two graphs is a bijection which maps vertices to vertices such that it keeps the adjacency relation and also in both directions. So it is there is an edge UV in the graph G if and only if the image pi u and pi v are adjacent in edge, and this map need to be an bijection. A very important problem is graph isomorphism problem. It is to say that if you are given two graphs, are you able to tell whether they are isomorphic or not? This is not an easy problem. So far there is no polynomial time algorithm known, and on the other hand, it is known that it's not prove that it's NP complete, and very likely I believe it's not NP complete. On the other hand, in reality, when people really try to implement the graph isomorphism problem, it is usually quite efficient. Only some very rare cases, they are kind of a very long time to tell whether they are isomorphic or not. The color refinement is kind of the simplest way to tell whether two graphs are not isomorphic, but it cannot guarantee two graphs to be isomorphic. So what is color refinement? Color refinement is such an algorithm, or you can call it a procedure. At the beginning, you color all the vertices of a graph the same color, just give a symbol to it. It doesn't matter what the color is, right? And then in each iteration, you update the color of each vertices. Formally, we update the color of a new vertices by the information that the color of itself in the last iteration and all the colors of its neighbors. This is a formal way to describe it. Or you can simply say in each iteration, we distinct the vertices by its color and as well as its neighbors. So here the double parenthesis denotes for multiset. And then we repeat the iteration until the partition induced by the color function on the vertex set is stabilized. Just is that for each colors you given to all vertices of a graph, it induces a partition by whether two vertices have the same color or not, then the procedure ends when the partition does not change anymore. This simple procedure is called color refinement, and it's in practice it's already quite useful for tell most people, most graphs apart. Okay, concerning color refinement, there are some equivalent characterizations. Here we would mention two of them. One is related to logic, and another is called related to linear programming. So if two graphs G and H can be is indistinguishable by color refinement, it is equivalent to say that they are indistinguishable in the logic FO-2. It is a two-variable logic with some counting quantifier later. We will talk about it in the next slide. And another way to say that these two graphs are fractionally isomorphic. We'll also tell what this means in the next two slides. The above results, they have generalizations, and it's called the Westphal-Lyman algorithm, more generally the k-dimensional Westphal-Lyman algorithm. And all these above characterizations, they have parallel and generalizations. So what is the logic FO sharp 2? So in this logic, we have the following components. We have equality relation, just whether the two variable you're using is the same vertex, denotes the same vertices, and the adjacency relation. And surely in your logic, you have not and all. And in this logic, you have the quantifier of vertices. This is the existential quantifier, and this is the for all. And what do we mean by quantifier is that you not only want something to exist, but also want something to exist, and the number, if it exists, is at least some number. So the first order logic on graph, it can be built by the A, B, and C. And when you add the sharp here, it means A, B, and C, D. It is actually equivalent to the first order logic on graph, because the last quantifier, you can expand it to other sentence in this logic by using extension quantifier, and it just become longer. So these two are actually the same logic, but the two here is kind of important in the calculation, is that it is a fragment of this logic, and you can use at most two distinct variables. And here variables are only to represent the vertices, not the set of vertices or any other things. This is due to its first order logic. Okay, and concerning the fractional isomorphism, it says there are something more about it. First, we know that two graphs are isomorphic if it can be characterized by its adjacency matrix, is that there is a permutation matrix P such that PAG equal to AHP. Also, you can put the permutation matrix on the right-hand side by putting P transpose. The linear fractionally isomorphic is the relaxation of the condition by replacing the permutation matrix by doubly stochastic matrices. As you can see, this too is simply by replacing P, the permutation matrix here, by S, the doubly stochastic matrix. There are also some related concepts, something called weakly quadratically fractionally isomorphic. If you consider the first definition, the isomorphism, you can put the permutation matrix on both sides. You can put them on the same side or not on the same side. So if you put them on the same side, then when you consider the entrances as variables, it kind of becomes the quadratic optimization problem. So here, it's called weakly quadratic isomorphic. G is weakly quadratically fractionally isomorphic to H if the adjacent matrix AH is AG by this transformation of the doubly stochastic matrix X. Also, there is the quadratically fractionally isomorphic if this relation can go both ways from G to H and H to G. And there is also strongly quadratically fractionally isomorphic if the above relation, in both directions you can use the same doubly stochastic matrix for the both relations. And the last one is semi-isomorphic, is that you use different doubly stochastic matrix on both sides. It was already proved by, sorry, I didn't write the authors. They are Everett and Landon, if my memory is correct. Maybe, oh no, it's the other author. Sorry, I should add their name here. Is that 3, 4, 5 they are equivalent. 3, 4, 5, and 1 they are equivalent, and 1 implies 6 and 6 implies 2. So this is about fractional isomorphism. Okay, so what does we mean by graphs can be distinguished by color refinement? Is that a graph G is called CR, is short note for color refinement. CR distinguishable if color refinement can distinguish it from any other graph, which is not isomorphic to G. So we call this graph G CR distinguishable. And later we need some notation for later displacement. So here I will talk about them here as well. So if G is a graph and X, Y are some subsets of the vertices, we'll assume that it's disjoint, then Gx is the subgraph induced on X, just the induced subgraph on X. And Gxy, since Xy are disjoint, here is the subgraph composed of the addresses between X and Y. So it's a bipartite graph. And the color classes of vertices obtained by color refinement, the final stabilized color, we will call those classes cells. So there have been characterization on CR distinguishable graphs. So what we know some local structure and global structure of these such kind of CR distinguishable graphs. If X is a cell in G, then Gx must be one of the following graphs. It's the complete graph, or it's complementary, just the empty graph, a perfect matching, or the complementary graph of the perfect matching. And there is a special one, the 5 cycles of 5 cycle. And we will later see that in digraphs, such characterization will be different. And the first case, type, we call it homogeneous, and it's the using by the original authors. First type is called homogeneous, and the latter two types are called heterogeneous. And this is the characterization of the cells, and what graph looks like between the cells. So if X and Y are two distinct cells, then the graph Gxy must be one of the following. it must be the complete bipartite graph or the empty graph, or it must be copies of stars, the same star, that is the star K1T, and you have several copies of them, or it's bipartite complement, just means you just reverse the adjacency relation between the two cells, not in the cells itself. And the first type is called isotropic, and the second type is called anisotropic. This is the local structure of the CR distinguishable graphs. And there are also something about its global structure. So we have reduced the problem onto the relations between all cells. So here comes the concept of the cell graph. The cell graph, you can regard it as a complete graph on all the cells, but you will label the vertices and edges by some homogeneous, heterogeneous, isotropic, or anisotropic. In this slide, you can see that the types. Then an anisotropic component is a maximally connected subgraph of the cell graph, whose all edges are all isotropic. And the characterization of the global structure is as follows. This is one way to characterize that. If you consider a component of an isotropic component, then this component must be look like this, is that in this component, you can find the one with minimum cardinality. The cardinality is the size of the cell, that is the number of vertices in this cell. Then for any path in this component, starting from this cell, the cardinality of cells must be non-decreasing. So it's either of the same size or become larger, or I suppose say the component must look like a tree. So there is only one way from a cell to other cells. The second one is B contains at most one heterogeneous cell, and if R is such a vertex, the heterogeneous cell must have the minimum cardinality among those cells. So the characterization of CR distinguishable graphs are that A, B, C, D, that above theorems give the necessary and sufficient condition for a graph to be CR distinguishable. So a natural problem is, how about digraphs? So color refinement on digraphs. Here we can consider two kind of generalization of the color refinement on digraphs. One way is that when you update the color, you consider the color of the vertex itself and its all neighbors. And another surely is consider itself, its all neighbors, and its in neighbors. So we will call them CRO and CRIO respectively, and we will give the characterization in either case. Here just we use the same words for those like CRO distinguishable and CRIO distinguishable. And since we need to consider some cells, the arcs between cells, so we need some notation for the directed graph. So if D is a digraph and the X is a cell, or you can also say a string subset here, then the induced subgraph is denoted by dx, and this one is different. So X and Y are disjunct subsets, or you can think of them as cells. Then this notation is that you consider all the arcs from X to Y. So you do not consider the arcs from Y to X, and also you do not consider the arcs between inside X or Y. And we also call those obtained by the stabilization partition, those color classes or vertices, call them cells. Okay, so first is what is CRO? Here we do not consider in neighbors. So first one, the local structure is that each cell, it must be either empty graph or complete digraph, empty digraph or complete digraph. So they are in the, if you only consider all neighbors, then it must also always be homogeneous. And between two cells, without loss of identity, let's say the size of X is no larger than the size of Y, then there are two cases. If the size of X is at least 2, then all the arcs from X to Y, it's composed of an empty digraph or the one-sided complete digraph. That is, you have all the arcs from X to Y, but not the arcs from Y to X. And if you look at the backward direction, says the arcs from Y to X, it must be always empty digraph, or you have all the digraph. So here you have kind of combination here. You can have empty, 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 complete, and complete, empty, and complete, complete. And these are all isotropic. Another case is that the size of X is 1, then there is one more possibility here. So the arcs from X to Y is either empty or kind of one-sided complete, or the discrete union of directed star and several isolated vertices. Just X has several arcs to Y, and there are also some vertices in Y which do not receive the arcs. And this case is called anisotropic. And the arcs from Y to X is the empty or the complete, and they are categorized as isotropic. So what about its global structure? The cell graph is it becomes a digraph, and we'll also label these vertices and arcs by homogeneous, heterogeneous, isotropic, and anisotropic respectively. Now we will slightly revise the definition of anisotropic components. We will use the maximally weakly connected subdigraphs, so whose arcs are all anisotropic. So what's the local global structure of CRO discriminatory digraphs? Is that first, if you take out an anisotropic component, then it must be a rooted directed star. Just you have all the arcs coming from one vertex. And the B contains exactly one singleton vertex as its root. And the above properties, A, B, C, D, they are necessary and sufficient conditions for digraph to be CRO distinguishable. Okay, the next one, we consider CRIO distinguishable digraphs. So we both consider in neighbors and out neighbors. And here you can see the difference from the graph case. First, the cells, it must look like complete digraph or empty digraph. This one is homogeneous, and you won't see the original perfect matching case. But here, the 5 cycle becomes the directed 3 cycle, and this case is called heterogeneous. And for the the graph between two cells, it must be empty or complete. And the other case in anisotropic is that it's also a disjoint union of directed stars. And X and Y are the S roots and the leaves respectively. Surely you can also consider its one-sided bipartite complement. Just to reverse all the relation from X to Y, but only inside X to Y, and you do not consider those from Y to X or others. Okay, how about the global structures? The global structure is kind of similar to the graph case. First, that is that still B is a directed tree. But let me emphasize that here, directed tree, it does not mean a rooted tree. It just means a tree, but you add directions on it. It is not necessary that all those directions are consistent. So suppose R is a cell in this direct tree of minimum cardinality. And now we try to give new orientations on each axis inside this directory tree, such that the directory is rooted at this cell of minimum cardinality. Then, if you start from this cell R to other vertices, the cardinality of cells is non-decreasing. And the second property is that B contains at most one heterogeneous cell. And if R is such vertex, it must have the minimum cardinality among those cells. And the above conditions, A, B, C, D, they are necessary and sufficient conditions for digraph to be CR-IO distinguishable. How about the other characterizations? Without saying about the details, but we like to say that for the logic case, we still have the same characterization. That is, you just only need to replace adjacent relation by arc. Here, be aware that you need to, for the color refinement, you need to consider both in neighbors and out neighbors. If you only consider out neighbors, this does not work. If for people who are familiar with the pebble game, because in the pebble game, the pebbles are kind of you need to consider all the arcs between the pebbles, so it's not enough to consider only the outer arcs. So here is another problem. How about fractional isomorphism? This seems that it's very different from the graph case, and we have not completed all the results to it. But we would like to say it seems that there should be counterexamples for the earlier case, which appears in the graph case. For the quadratic cases, they seem to, in most cases, they are still equivalent. But for the linear cases, they are. We expect some counterexamples, but we are still constructing them. And so these are all my talks. Thank you for attention.
Thank you very much for your talk. Any questions to the speaker?
I have a question.
Yeah, sure. Yeah. Please, Oleg. Yeah.
So your theorem A in page 14 seems a bit surprising to me because I would expect that in this model, this should be a generalization of the case of undirected graphs. And so, okay, in particular, if we consider a directed cycle of length 5, so isn't this a counterexample to this theorem?
If you have a directed cycle of length 5, you can consider replace it by direct cycle of length 3 and a direct cycle of length 2. Well, it's kind of it's a little bit ambiguous here because if you are consider kind of the
I see. I see.
Yeah.
Okay, and I have one more comment. So the second definition of color refinement, I think it was considered in a paper by Kiefer-Schweitzer and okay.
Thank you very much for the information. But I studied because I didn't discover, so I kind of.
So do you know this paper or not?
Sorry, I don't know. Please, could you say that again?
Okay, I will send you a reference in a minute via chat. Okay.
Okay, thank you very much.
Okay, thank you.
Thank you, Oleg. Are there any other questions to this?
Can I ask? Because
Yeah, sure, of course, please.
Maybe Oleg told me, because in my mind, all these results were proved in Pascal paper. Is it true?
Could you pardon? I didn't hear it clearly.
No, I think that at least this weaker version of color refinement, I think, was not considered there, and maybe it's quite interesting to look what changes in the weaker model.